I'm going to play the cleanup hitter, I guess. What I wanted to do here is give you some update on some things that we've done over the last several, I'll say, decades here. And what we want to do is kind of show you what's the impact of all these if you implemented a bunch of these practices. So one of the first things I'm going to talk about is a project that we worked on for actually a whole decade. And in the early 1990s, actually some people from the USDA came to 5 universities in the Corn Belt and said, you know, you people have been telling us all these years about if you did these things, it would help. And they said, prove it, okay? So if you go out and we do all these different things, what impact is that going to have on groundwater quality? So one of the marquee sites in Nebraska, I'm going to say MSEA, stands for Management System Evaluation Area. It was located in just outside Shelton, which is about 20 miles east of Kearney, about 2 miles from the Platte River. We picked this location. It's obviously very intensely farmed and irrigated. The water level there, the groundwater is relatively shallow, maybe 20 feet thick or something like that. And then we installed, you see these little dots there, we installed, Roy Spalding installed, this is a very interdisciplinary group. I mean, we had about every discipline you can think of involved. But Roy installed monitoring wells where we could look at the concentration of the water in at the bottom of the crop root zone, between the root zone and the top of the water table, and then in the groundwater. So by picking this location with a shallow water table, we were able then, over a decade or so, to see what difference these practices might have made on the groundwater below the site. We had, so in this particular part of the study, we had an entire quarter section of a field, and it was divided into 4 different management practices. One was what the farmers conventionally did there, which was surface irrigation and relatively high fertilizer levels. We had one site where we surface irrigated, but we used a technology called surge irrigation, which really improved the performance and efficiency of the surface irrigation. We had one that had a center pivot on a quarter of that quarter section. And then we had a quarter of that, or 40 acres, that was actually alfalfa that we raised on a continuous basis. So I'll show you a little bit of the outcome of some of this. Now, why did we pick that spot? We're looking right in here. The nitrate concentration, the red dots are anything above 20. Our concentration of the groundwater that we pump ranged from about 25 to 32, 33 parts per million of nitrate nitrogen. I'll also talk about some work that we've done out in the western sand hills, looking at the potential of nitrate management in those very sandy soils. And it relates to some work we did over by Elgin also during that time. Now, I also want to make a comment here. These green dots are areas where the concentration of nitrate nitrogen in the groundwater has not yet reached that 10 milligrams per liter or 10 parts per million. But some of the studies, and associated with part of what Charlie talked about, is some colleagues have done some deep core sampling from the soil surface all the way to the groundwater at the South Central Ag Lab. And then they went through, and those cores analyzed how much nitrogen is in that entire zone above the water table. There's a huge amount of nitrogen in that, what we call vadose zone, that hasn't reached the water table there yet. It's moving downward at a relatively slow pace. So we may think here where these green dots are, we're home free. But I'm telling you that there's a whole bunch of N that's headed that way. It's just going to take a while before it gets there. So we should not be so complacent to think that we don't have issues where we see green dots today, perhaps. Well, sorry for some of these slides. I couldn't get better ones out of the publication. This is what the farmer did in a 5-year period from 1991 to 1996. And so what you're showing here is the amount of fertilizer, the amount of nitrogen from fertilizer, and then the irrigation water. So these horizontal lines are what he put on as fertilizer. The dashed lines are the amount of nitrogen that was in the groundwater that we pumped. The little dots across here are what we would have seen that needed to be, how much fertilizer you need to apply if you use a nitrate-free water. So this is the fertilizer level if you had clean water. This is how much you got out of the fertilizer. So you saw he fertilized to a level where he ignored the nitrogen in the groundwater. The amount of nitrogen in the groundwater was several hundred pounds. This guy irrigated a lot, I'll just say that. This was our surge system where we had very carefully managed surface irrigation and a little bit better managed, or certainly better managed fertilizer. We used the chlorophyll meter to monitor the concentration here. We tried to chemigate on surface irrigation. That's a challenge, which you can see now then that we have greatly reduced the amount of groundwater nitrogen that we pumped. We pumped a lot less water in that setting. The one on the right here then is what we had for our pivot system. And so, you can see 1993 in here, if you all remember, 93 was the really, really wet year that year. So we had very little pumping at all. So you can see the differences that we had in terms of total nitrogen in the system. This is looking then at the concentration of nitrate nitrogen below the root zone towards the end of that 10-year period. And what you can see is with the sprinklers, we're actually, sorry, I think I'm shooting inside the head here, thank you. We're actually, with sprinklers, we're actually getting that concentration maybe below the 10 milligrams per liter. That would be our goal. With well-managed surface irrigation and a relatively high level of nitrogen management, we weren't able to get below around the low 20s. Doing what we're doing today on some of these locations, the concentration was up to 40. So it's no surprise that we have very high nitrate levels if this is what, more than this individual was doing. So kind of the take home here, yeah, we were able to really make some differences there. This is a real bad slide, but let me see if I can walk through it. This was looking at the nitrate concentration, and I want to look at the brown line that goes across here. This was the conventional corn. Now this is highly tilled because it's surface irrigated, so it had to be ditched. So you can see that we had a dip in here in 93 because it was so wet, but we pretty much ended up where we started, and we're in the mid-20s to up to the 30s. It's not as high as we measured below the field because not all of the groundwater there is underneath a farm field. If we look at the nitrate below the intensively managed surge and surface irrigation system, we saw some drops, but quite honestly, it didn't do as well as we had hoped. This is what we saw with the pivots. And so what you saw with the pivot, we started out in those high 20s. We really dropped to 93 because we had a lot of leaching that year, and it kind of came back. And so we ended up actually getting the nitrate concentration down below our goal, okay? So, so maybe the message to these agencies is, yeah, we can get there. Now, I don't want you to think that it's all because of center pivots. This was a system that we put together. We used a chlorophyll meter at the time to monitor the nitrogen status of the plant. So we're using the plant as our indicator of how much fertilizer to apply. We put on some small amounts of starter to start the season. Most of the nitrogen during the year was put on with chemigation through the center pivot. And so we're basing that amount and timing of nitrogen on what the plant is telling us it should be doing. We monitored soil water very carefully. This just is an instrument we use to measure soil water very accurately, so we scheduled very carefully. So in order to get to that point, we had to put all this technology together. I also want to think a little bit about looking at kind of a nitrogen balance. If we look at our field here, on any field we have, we're going to have some non-point nitrate leaching from a field. It's just inevitable that we have some of that. After it leaves the bottom of the root zone, this is what we call the vadose zone. It takes a significant amount of time for that leachate to reach our water table. Some studies from the sandhills might say that material is moving 5 to 7 feet per year through that vadose zone. So if you have 100 feet in here, what you did today might not show up in the groundwater for another decade or two. Well, this nitrogen then accumulates in the groundwater. And the only way that I really know of that you can clean up the groundwater is to pump it back out for irrigation. And so if we have to think about the change in groundwater nitrate is really a mass balance question. How much nitrate do we pump out versus how much do we leach in on an annual basis? And so over the long haul, if we can reduce this one, we've heard a lot of talk here. That's not the right way to, yeah, I guess right. We've heard a lot of talk here about all the different ways that we can go about improving nitrogen use efficiency. That ought to relate to reducing how much N we're going to be leaching into that. And all of these are wonderful ideas that weren't included in some of what we did. We have to think about the nitrate that we're pumping out of the groundwater, and our studies, quite frankly, would show if we don't account for that and making adjustments to your fertilizer recommendation, we're still going to be polluting, so to speak. And so if we look at this is just looking at what the nitrate concentration might be of the water, and this is the amount of water that you would apply. If you put on 12 inches of water on average and maybe had 10 milligrams per liter, that would be about 27 pounds of nitrogen per year. I believe the gentleman a while ago said they might be at 30. So in that case, you're getting, 80 pounds of N out of the groundwater that you're pumping. And if we can use most of that in our system, one, we can help clean up the groundwater. Two, we can save some dollars even in today's poor economics and grain. We also did a lot of simulation work in looking at, well, what happens if we just pump excess amounts of irrigation water then? So one would be just doing a very good job of scheduling. 1.5 would be if we put on 50% more, and 4 would be if we put on 4 times as much water. So this is looking at the amount of nitrogen taken up by the plant. So in this case, at this location, we had 25 part per million of nitrate in the groundwater, and we had 45 kilograms, which is about 50 pounds per acre of fertilizer applied to the plot. So very low fertilizer level. Our total nitrogen uptake is somewhere above about 170 kilos per hectare, just about the same as pounds per acre, so around 180 pounds per acre. In this area, we probably need, at this time in these crops, we probably needed around that 190. So probably in here would be where we'd meet full yield. So when we look at this with 25 parts per million, if I put on twice as much water as I needed, the fertilizer contribution is insignificant almost. We get a tremendous contribution from the groundwater, and then we have mostly mineralization that's coming out of the soil that's supplying that need. So what our studies showed is that, yeah, if we pump more water, we can certainly extract more groundwater, and we wouldn't want to put much fertilizer on if we did that. What's the problem here? The problem is, how much does it cost me to pump this extra water? Now, when we're in the Platte Valley, that water table is very shallow, so the water is pretty cheap. If we get into some upland areas where that water table maybe is 100 feet low, below the land surface now, it's going to cost me, that cost to N might be a little bit higher. This is showing that, yeah, we can pump more water and we can extract more nitrogen. This is a complicated slide, but this is looking at the concentration of the groundwater. And one concept I'd like to have you think about, sometimes we make this be real complex, but if we're going to haul more nitrogen away from the field than we hauled in on fertilizer, I think we're purifying. If we haul more fertilizer in than we're hauling away in grain, I think we're still in the pollution mode. So I kind of break this down as here we're in the pollution and here we're in the purification. So this is an example of where we had a very low fertilizer rate, 50 pounds per acre. We had to get above 20 parts per million at this site. This is that sand hills in the west. We couldn't get enough N to make full yield at 45 or 50 pounds per acre until that concentration gets above 20. And then by over irrigating, we can enhance that uptake. So when the take home, this is when we put more fertilizer on. We went up to about, what are we at? About 150 pounds of fertilizer in total there of nitrogen. We never get into the purification mode. We're always in the pollution mode, okay? So we can purify with this system, but boy, you have to really tie groundwater into fertilizer to achieve it. Let's think a little bit about what's driving some of this system. This is just pick some data over at Albion, which is what, about 50 miles southwest of here, right? So this is the average monthly rainfall at Albion. Our most rainfall is, of course, early in the spring. This is the amount of evapotranspiration that a corn crop would use. And so when I superimpose those, and this gets back to what Charlie was saying before, I believe, this is the amount of water our crop needs. This is when the rain occurs. So this period in here is a time that, one, we can refill the root zone, but it's also a time that we see significant amounts of deep percolation of nitrogen if it's available in the nitrate form at that time. What we're able to do with chemigation is move that fertilizer application till later in the growing season, and we avoid this leaching, especially on our sands. This that we see in some of our work, we'll see 75% of the annual leaching loss occurs before I ever irrigate, okay? And that's because we have these heavy spring rains. So we have to get the nitrogen either tied up with the inhibitor, maybe some of the cover crops gets it into a biological form that's not leachable, or maybe we just don't put it on and we get it back into the latter part of that season. We know how the crops take up nitrogen. So if we superimpose, in our case, this is kind of the rainfall pattern, this is a crop uptake pattern, and this is our potential leaching period because it's raining more than we're using in the crop. Well, that work was done in the 1990s at the MESA site. What's happened since then? Well, we've got way, way, way better technology that's easy for producers to get to monitor soil water. So more producers ought to be able to really manage their irrigation water better than we could have in the 90s. This is looking at the computerized controls we now have. I'm stealing your slide, Bill, I think. But this is looking at our ability now to control our center pivot to do exactly what we want. If we get a big rain, it rained on me hard when I was driving up this morning, I could just turn the pivot off by my cell phone if I want to. So we're building that kind of control into these systems. So if we think about kind of where we were at, kind of stage one, we had to know what the plant's going to require, and we had to know what the soil nitrogen was. And this used to be what we based our recommendations on. We learned that we could maybe go out and get some point measurements of plant status, and we could improve our fertilizer management by achieving that. Mentioned earlier today, now we're moving into looking at how we can now maybe utilize, this is using a floater, this is using our drones, some people are using the center pivot itself as a way to map the nitrogen demands across the field so that we get a spatially and temporal, real-time measure of the crop status for nitrogen. We aren't there yet in terms of finding something to tell us what the water status is of the plant, but we got a lot of really smart people working on this. So kind of where we're headed with technology is this ability to get, build on the fundamentals, get reliable information that tells us where we're at today. We can feed that into a chemical application system. These probably have to be more robust than what you're normally seeing because we're going to ask more out of the ability of these devices at times to put on lots of fertilizer and other times to put on very little. And now then we can combine that with our variable application technology so that we can vary the water and nitrogen as we go around the field. Surely, now this technology is expensive. I'm not saying everybody can afford this today, but the direction we're really trying to go is we ought to be able to do a lot better. We ought to be able to get below 10 parts per million in this system if we pull all of these things together. My family, we still farm in southwest Nebraska. I tell people, my brothers, I'm the absentee landlord. I'm not as absentee as they might like. But I fully understand your concerns about how busy the farmer is. And so the more we're able to get this integrated into a system that fits their schedule, then the better off I think we're going to be. Again, I'd like to have us think about, are we polluting or are we purifying? And a very simple way is how much nitrogen are we hauling away and how much are we hauling in? Now I can apply that to a field, I can apply that to my plot, I can apply it to this watershed. I mean, if I'm raising all the grain and I'm feeding the cattle and all that's within the watershed, I don't think the cattle added anything to the groundwater pollution. You know, it was the nitrogen we hauled in for the grain most likely. So in a lot of cases, maybe you have to add in here crops that fix their own nitrogen. But in a lot of ways, in a simple concepts, how much you're hauling in, how much you're hauling away, am I making it better, am I making it worse? Okay, last thing I wanted to say here is, let's think about the time period here. So we talk about a saturated thickness of groundwater. That's the depth of groundwater that's in the aquifer, the sands and gravels that we have out there. And so let's look at an example here. Maybe I have an aquifer that has a 100-foot saturated thickness. Let's assume about half that space is air space. We call it porosity. So it's pores that are holding water. The rest is gravel and sand. And maybe, let's suppose we can remove 50 pounds per year of nitrate nitrogen from that groundwater system by managing how we fertilize and irrigate. How long will it take to reduce that concentration by 10%? Okay? So the amount of water that's below us in an acre is 21 million cubic feet. The amount of nitrogen that's in that aquifer below us is about 1,350 pounds of nitrate per acre. So to reduce this concentration 10 parts per million, it would take 27 years, okay? So even doing very, very well, we are not gonna change that water concentration in the groundwater real fast. And I think we have to be focusing on drinking water, other kinds of treatment facilities that we're gonna have to rely on as we go forward. I don't think we have that technology is pretty good. We don't have real good technology in monitoring how well those systems are doing, so the homeowner may not have that in place. But this was kind of a dynamic we have to live with. And now if we have another decade or two for it to go from the bottom of the root zone before it gets in here, you know, we could be looking at 30, 40 years before we make changes in that nitrate concentration. I think that's the last thing I had. I would just suggest, if you're interested, this is a publication a group of us, a broad group of us worked on, developing some guidelines here to how you might manage irrigation and nitrogen. You can either buy a nice copy or you can download it if you want. Maybe if you haven't seen it, it might be worth taking a look at. There are a lot of tools out there, folks.